Okay, so today we are going to study about rotations and orthogonal matrices. So the we are going to be talking about several equivalent statements and the how to go about proving them, appreciating the properties of orthogonal matrices, how they are connected to rotations. So, but the important thing is that to understand the central message. Central message ultimately is essentially the theorem which says that rotations of the plane or in three dimensions about the origin are linear operators whose matrices with respect to the standard orthogonal standard basis are orthogonal and have determinant 1. In other words, a matrix A represents a rotation of the plane or in 3D if and only if A is an element of SO2 or SO3. So we are going to define all these terms, don't worry about it, but that sort of is the punchline of this lecture. Right at the front, that there is an intimate connection between rotations and orthogonal matrices. So, okay, now we come to how do we go about constructing this. So first of all, what exactly are rotations? So what are rotations? So essentially, we already noted that an object like this in the last lecture uh, it represented a rotation. So this was rotation of R2 by an angle theta, and that can be represented as multiplication by the matrix. How do we define a rotation? So this was essentially the rotation of the whole plane. So you have x, y. This would be now your x prime, y prime. That would be your angle theta. The whole plane rotates. Now, for R3, rotation of R3 or any three-dimensional rotation can be described by an axis and an angle. That essentially it is to it. So this is a unit vector or the axis of rotation, and this is the angle. And that is all there is to it. Uh, and you can also say that this rotation is equivalent to this guy, the opposite direction and the opposite angle. So they think about it, they represent the same rotation. And in general, uh, it's easy to see that the matrix, for example, matrix representing rotation through the angle theta about the vector E1 is obtained easily from the 2 cross 2 rotation matrix. So, which is to say, just stare on this matrix a bit. Let's say I'm focusing on rotations about the x-axis. So, here is my 2 by 2 rotation. What I do is that I fix this guy, and now I'm only interested in rotations about this particular axis. So this ensures I'm fixing x, and this ensures that once I fix the axis, this is a rotation of the plane, the zy plane. So that essentially is a rotation. You can check it. This particular thing is going to leave the x coordinate of a vector x, y, z will go to x, y prime, z prime, and it will be basically a rotation about the x-axis. So that was just an example of how, at least in one example, how the rotation matrix turned out to be a matrix of a particular point, rotation about the x-axis. But essentially, there's nothing special about one particular rotation, so to speak. It can be any axis. And that is central message of this lecture, that rotations in general are some special matrices or SO3, which we'll be talking about. That is all there is to it. So what do we have? So a real n by n matrix, we are going to define what SO2, SO3 mean. A real n by n matrix A is called orthogonal if A transpose is equals to A inverse, or you can say A transpose A is equals to the identity matrix. And these orthogonal matrices, you can check, they form a of subgroup of the general linear group of n by n matrices, general linear group of n by n matrices which are invertible. By group, I mean they will have an identity element, they will be closed under the conjugation or composition, law of composition. The product of two matrices will also lie in that particular group. And you can check that the determinant of an orthogonal matrix is plus minus 1. Because A at equals to I, and then, well, the determinant can factorized as a product. So basically you have determinant of A, the whole square is equals to determinant of A, determinant of AT, because the determinant of the transpose is the same as the determinant of the matrix, original matrix, and that is equals to 1, and hence the determinant of A is either plus 1 or minus 1. Okay, so the orthogonal matrices having determinant plus 1 form a subgroup called the special orthogonal group denoted by SON. So SON is a subgroup of the general linear group of invertible matrices such that the matrices are orthogonal with the determinant 1. Okay, now what do we have? Our task is to now, so one way to look at it is to appreciate that how simply we have been able to describe rotations by elements of SO2 or elements of SO3, at least in the plane or the 3D rotations are concerned. And since they form a group structure, you can combine any two funky rotations, and the product matrix is also going to be a matrix. So rotation 1 times rotation 2, and the product is also going to lie as another matrix which is going to be orthogonal with a determinant of plus 1. So this is a very elegant way of representing any rotation or composite rotations. And mind you, the beautiful thing is that they do not need to be about the same axis. So I can assume about the same axis. So I can assume I have an axis, let's say the axis is pointing down towards the plane. So I can say that, okay, these are two rotations which are composite rotations, and I trivially am able to essentially say that the sum of the composite rotations is a rotation about the same axis with an angle 2 theta, but this thing holds for a rotation about any two axes, and it's going to be a rotation. It's a pretty non-trivial observation. It's very simple in 2 dimensions we can see in the plane. 3 dimensions we've already conjectured. So the story for the rotation groups in higher dimensions is not that obvious. So for example, for SO4, SO4 would be special orthogonal group of 4 cross 4 matrices with determinant 1. And that group is like cosine theta minus sine theta, cosine neta minus sine neta, sine neta, cosine neta. So this is an example of an element of SO4. This is an example from your book, essentially. And well, this is in SO4, but this is basically a rotation of the first 2 coordinates and a composite rotation of the last 2 coordinates. This cannot be described by as a single rotation. So the things are, I would say, much simpler till 3 dimensions. 4 dimensions, the SON group beyond 4 dimensions acts a bit funny. So basically, the rest of this section in the book is essentially boils down to exploring the relationship between orthogonal matrices and rotations. Notice we already had one example where we had a glimpse of it. These guys, if you can check, are orthogonal matrices and they were basically rotations. Same with this particular guy out here. But in general, what is the connection between rotations and orthogonal matrices? So for that, to develop this sort of an intuition about it, we need notions of a dot product. So what's a dot product? Dot product is essentially, now we are adding, remember there was a question in the first class that, hey, what about the dot product and inner product and things like that. So now we are adding more structure to our vector space because we want to do things like, we want to maybe measure things, we want to define norm of a vector, length of a vector, because those things are going to be physically more intuitive, and that's going to give us the intuition of what the heck is going on. And then there was this question, how did this vector spaces came? Well, vector spaces is our construct. We are adding more and more structure to the vector spaces so that it is useful. So now we define a notion of an inner product or a dot product that's going to help us characterize what the heck is a rotation. So we observe a physical phenomena, we develop mathematics, we keep putting structures in the mathematics. So that's sort of is the philosophy. So this is the DOS product, and why we need that is that because we want to define a notion of distance or length. How so? So the main properties of the dot product are that well, you can have x dot x, and that is just x1 square plus x2 square xn square, something like that. Or you can have so this is the notion of a length or the norm of a vector, or I should say length squared or something, doesn't matter. You can also have a notion of the distance between two, or the length of x minus y, of vector x minus vector y. And the other important property of the dot product is that dot product of two vectors is nothing but x magnitude of y times cosine of the angle between them. So this also you can prove through geometry, law of cosines or something. So just figure this out, not very hard. So these are the two properties of the dot product which are going to be useful for us. Okay, so now we come to why are we doing this? We come to the proposition. Of course, you can say that the vectors are orthogonal if x dot y is 0 or the dot product is 0. Okay, so the following conditions on a real, so that's the proposition now. We defined the dot product, let's use it somewhere. So the proposition says that the following conditions on a real n cross n matrix A are equivalent. A is orthogonal, multiplication by A preserves the dot product, and what else? Columns of A are mutually orthogonal unit vectors. Okay, so we can easily show these things. Well, if A is orthogonal, uh, certainly A is going to preserve the dot product in the sense. Uh, so what is condition B? Condition B is that AX dot AY is X dot Y. And how do you show that? You start with, let's say, X dot Y, and then you can say that this is nothing but X transpose of Y. That's the definition of the dot product, which is going to be X transpose A. Let us write it as A because this guy was identity. So I'm just stuffing in the identity between them. And what is this? This is nothing but our proposition, which is nothing to say that A dot X, sorry, AX dot AY. So you can go this way, you can also go this way, simply by starting from this guy and we can start from this sort of a condition and we can go the other way. You can assume X transpose of Y is equals to X transpose of AT A Y. There's no need to assume, this is sort of true. And then from this sort of a condition, so we can write this as X transpose, let's say X transpose B of Y is equals to 0. just get this to the other side. So this is going to be equals to x transpose y minus x transpose A transpose A y. This is equals to 0, where B is this particular matrix. B is identity minus A transpose A. So essentially, I have a matrix B which accomplishes this task, uh, which is to say that for all set of vectors, uh, let's say the orthonormal vectors EJ, EI transpose times B times EJ equals to the matrix elements of the vector, and this is equals to 0 for all IJ. And well, what does it mean? This essentially means is that B as a matrix whole is 0. So this proves the equivalence of A and B, that the matrix is orthogonal, it preserves the dot product. Something that preserves the dot product is an orthogonal matrix. We can prove the C also, that the columns of A are orthogonal vectors. Well, simply you just stack up the columns V1, V2, V3, V1, V2, V3, and you have V1, V2, V3, the transpose guys. So what does it do? This is basically the matrix multiplication, and that can only happen when the columns are essentially mutually orthogonal unit vectors. So this has to be identity. This has to be an identity matrix because this is some A transpose times A. So that means that V1, V2, and V3 are mutually orthogonal unit vectors. Okay, so that way we prove the equivalence of A and C. You can start with columns of A being unitary orthogonal vectors uh, and get this sort of a condition, or you can start with the A being an orthogonal matrix from this sort of a condition and show that these vectors are mutually orthogonal. It's an equivalent statement. So the bottom line is that now we had a notion of a dot product and we started finding it useful. It let us define certain properties of or certain equivalence between orthogonal matrices, something related to the orthogonal matrices that preserves the dot product, so on and so forth. So slowly we are getting there. So essentially, the geometrical meaning of multiplication by an orthogonal matrix can be explained in terms of rigid motion or rigid body motion. Essentially, rigid body motion is you take anything and it you either rotate it or translate it. It sort of preserves any sort of an operation. It preserves the distance between 2 points. That's your rigid body motion. So this is a rigid motion, and the rigid motions which we are interested in is rotations and translations. If you translate an object, it's a rigid body motion. When you rotate an object, it's also a rigid body motion. And essentially, one of the central ideas of this lecture and the section of the book is that every rigid motion essentially has the form ax plus b for some orthogonal matrix and some translation. So any vector x, for example, I add some vector b to it, that's a translation. Essentially, this is what this picture describes. This is some vector x, I added some vector x, and this is, I get x plus b, which is essentially preserving the distance between two vectors, but it's still a translation. So that's a translation, and we've already seen a connection between what we are discussing, orthogonal matrices and rotation. So any rigid body motion or a rigid motion is a combination of a rotation and a translation. That is one of the central messages. They've gone about proving it, but more than the proof, the central message is more important. And how do we then define what's the connection between a rotation and a rigid motion? For that, there's a proposition. Let M be a map from vector space to the same vector space, and the following conditions are equivalent. M is a rigid motion which fixes the origin. M preserves dot product, that is applying M and taking the dot product is same as taking the dot product. M is left multiplication by an orthogonal matrix. So I hope you are appreciating the connection. So we have something called as rotations, which we said was connected to or was a subset of rigid motions. Rigid motions that fix the origin are described by orthogonal matrices, and we had a connection between orthogonal matrices and rotation. So that sort of is the logical flow. And why needed we to go in such a roundabout way? You can just state theorem at the start of the lecture, what we said as a theorem, that there is an intimate connection between rotations and orthogonal matrices. Well, we would like to ideally define what exactly is a rotation. Rotations can be characterized as rigid motions which are mathematical structure behind them is orthogonal matrices. So that sort of is the idea. You can prove these propositions, they are in the book, but and the arguments are very fairly similar, but I hope the central message is clear. Just read them, how they go about proving these propositions. So the take-home message of these guys, and even this result, that any rigid motion is essentially uh, a combination of an orthogonal matrix applied plus some sort of a translation, is also given in the book. So these are just simple logical arguments or extensions. So what is the corollary? The corollary or the upshot is that rotations of R2 and R3 are basically rigid motions which fix the origin. Not only that, They are also, remember, orthogonal matrices, as we described, let's say O3 or O2 or On, they have a determinant is, let's say, plus or minus 1. And we also said that we are interested in the group SO3 or SO2, which are set of those matrices which have determinant equals to 1. So what happens to minus 1? Well, we'll see that when you describe rigid motions, they can be either orientation preserving or they do not respect the orientation. Rotations preserve the orientation. So the orientation of 2 points or any sort of set of points, that essentially remains the same, and they are described by the matrices with determinant 1. And that's why we are interested in the group SO3. So I can add to this the rotations of R2 and R3 are rigid motions which fix the orientation and are orientation preserving. Okay, so one more reason for having the determinant to be plus 1 is that, well, what happens when the angle is 0? You know, rotation with 0 angle. 0 angle. Well, that's just the identity matrix, right? Nothing happens. And since identity matrix has a determinant of 1, and you want this to be a member of your family of the rotation group, that's why you're dealing with the any small rotation or any continuous rotation from a 0 rotation by a small angle has to be continuously deviating from the identity. So uh, that's why you need identity, which is rotation with a 0 angle, to be part of the family of rotations. And you can regard rotations as a continuous departure by a small angle from the identity matrix. That's why you are interested in the family of rotations with preserve the determinant equals to 1. You can also prove conversely. So why should I bother about? So these are all sort of equivalent statements, which is sort of very clear. So uh, essentially, what is happening? Uh, why should I consider any matrix element of say SO2 2 by 2 orthogonal matrices of determinant 1? Uh, well, they are rotations, as we already saw that we can write the matrix A describing such a rotation as when we started, right? We started with this cosine theta. So that was some sort of a vector. So essentially the idea is that let A be such a matrix. Forget about this. This is just some R. So what does it do to, uh, and let's say A have some column vectors v1, v2. I can always write this column vector v1 as some AE1. So or I can write this column vector as some RE1. or something like that. And since this is a just a second, let me just gather my thoughts for this. What I'm trying to say. Yeah, so there exists a rotation which goes hits a standard basis vector E1 or acting on your column vector, which gives me V1. Okay, and why do I know that? Because since A was orthogonal matrix, these are also unit vectors, unit vectors which are orthogonal, and this structure R E1 is going to have those properties. Now, since A is an orthogonal matrix, the other vector is either so I can take an inverse over here. So R E1 was V1, R inverse V1 was nothing but E1, and this is also an orthogonal matrix. If R was an orthogonal matrix, R inverse is also an orthogonal matrix. So the other vector has to be either E2, R inverse V2 has to be E2 or minus E2, nothing else. And since we are interested in matrices of determinant plus 1, it better be E2. So that way you can show the equivalence starting from an A, which was a member of SO2. This better be connected to a rotation matrix, and it is just doing the rotation or undoing the rotation. That sort of is the idea. The equivalence between A member of SO2 and some rotation which you already know was of this particular form. How do we show the same sort of a connection? This is just the last part of this lecture is how do we show the connection between a member A being an element of SO3 represents rotation. Well, so for that, what exactly is a rotation? A rotation is nothing but it's a rigid motion, as we have seen, that fixes the origin. It also fixes a non-zero vector V, which is our axis. Operates as a rotation. So once it has fixed that vector, this operates as a rotation on the plane orthogonal to V. So once you fix the axis, then it is just boiled down to the rotation of the YZ plane. That was sort of our idea. So, well, the first condition we've already shown, this was equivalent to A being an orthogonal matrix. So there's a connection over here. Well, how do we make sure that this sort of a matrix fixes an eigenvector? Oops. This fixes an eigenvector. Well, that can be, or this fixes some non-zero vector V if we show that this is an eigenvector. So by this we can show by showing that V is an eigenvector for the operator with eigenvalue 1. And the condition 3 it says nothing but once we have fixed the axis, then this operator is a rotation about this axis. So, you know, how do we prove that V is an eigenvector with eigenvalue 1? We just prove that any element of SO3 has eigenvalue 1. And the proof is rather simple. we can just write it as, so determinant of A is nothing but the determinant of A of transpose. We know that for matrix A. And then uh, what else do we have? So we also know that we are considered matrices with determinant 1. So since A is orthogonal, A transpose A minus identity is nothing but A transpose A minus A transpose equals to identity minus A transpose is equals to identity minus A transpose of the whole matrix. So now we can show that the determinant of A minus I is equivalent to determinant of I minus A. How do we show that? The determinant of A minus I is nothing but determinant of A transpose A minus I, and that's because the product, determinant of product is the product of the determinant. This is nothing but from our above thing, determinant of I minus A transpose. Just figure this out yourself, which is equals to determinant of I minus A. So I have a matrix B, let's say, whose determinant of that minus is equals to determinant of, in general, I have this guy, determinant of B minus. If I put the minus sign, I get this thing for a 3 by 3 matrix. So therefore, what do I have? I have determinant of A minus I is equals to minus or determinant of I minus A. And I've already proved that these guys are actually equal. So the only way it is possible, the determinant of A minus I is 0. So essentially from our characteristic polynomial arguments, I note that the eigenvalues are 1. And that actually tells me that there is an eigenvector that gets fixed through this sort of a matrix. So then we are done. We have characterized three-dimensional rotation through SO3. We know it is fixing the axis, which is the eigenvector. And then it just boils down to a rotation about that axis. We already saw that, we saw that in the case of a rotation about x. This was the eigenvector. And then we had nothing but our rotation about that particular eigenvector. That is in general true for any SO3 member. If you have the vector that gets fixed with eigenvalue 1, A prime has a block form. So this gets into block, and this is R, where R is a member of the planar rotation, and this guy A prime is a member of SO3, and this would be my eigenvector in some basis which gets actually fixed if I choose that eigenvector as a basis. So that sort of shows you everything we need to require over here. We have proven the equivalence of SO2, SO3 to two-dimensional rotations or rotations in 3 dimension, and we've known a way to connect this all to motions in rigid body in general and things like that. So read this chapter. Thank you.